first, thank you for coming. Obviously, my name is Michael Rees. I'm a program manager on the big data team. Here's my contact information. If you want to tweet at me or send email, please take a photo of it. That's the last time you will see that. So now let's go and talk a little bit about what we want to cover in this session. So the main objective here is that we really want to understand some common best practices on how to write efficient uSQL scripts in Azure Data Lake Analytics, that we understand how uSQL query execution actually works, and use that knowledge then to basically optimize both the cost as well as the actual execution of a script. And we'll show some examples, and I will also sometimes use examples that I actually have seen customers do wrong, or see people ask questions about, for example, on either internally or externally, for example, Stack Overflow. The key takeaways that I hope that you will get is that uSQL is really designed for scaling out over large amounts of data, and that it gives you a scalable execution framework for your user code, and that it has a lot of interesting tools that can help you analyze and improve the scalability. In particular, here is like just a few of the items that I have in the deck that I want to cover. First, I will introduce kind of the job execution experience and framework, then show you how to actually analyze a job, how you can like use the tooling in Visual Studio to take a look at the job and better understand what's going on. Then also do some job performance analysis, and I will use one of our own 7-hour, several terabytes of data jobs that we run inside Azure Data Lake in our telemetry system to kind of exemplify that. And then I will go into how we can actually use the tooling to do cost analysis of a job and try to see what can we do to improve the job. I will also cover some of the kind of common misconceptions about how AUs correlate to parallelism. And then in the last section, I will basically just go through some tips about how to tune your uSQL script. Like, what are some of the gotchas that you might want to run into? What are some of the tools that are available to help you tune it, including some hints? So this is really a 400-level session. Some people might think it's a 500-level session. So if you feel that I go too quick, or if you have questions, please wave your hands so I can see it. It's a little bit hard here with the lights. And I will see that I can answer it, or at least take it back. So let's first look at the uSQL query execution. A uSQL script, how many of you have seen or written a uSQL script yet? Good. How many of you are completely new here and have never heard of uSQL? This might not be the best session for you guys. Just a hint, you might want to come in my session tomorrow that is much more like geared towards how to see how uSQL works. So uSQL basically as a script is a bunch of SQL-like statements, and you basically put them into a simple script. Can show you one that I will show later. Here, for example, is a simple join statement. I do some, zoom in a bit. Here I have some TPCH data. I basically schematize here some files for line items and orders. And then I do a join here, and then I output. So this is a very simple script. It only consists of four statements, 2 schematization statements, plus a join, and plus an output. However, unlike in like T-SQL or Hive, where each one of these statements would get executed individually, a result would be generated, and then it would be passed on to the next statement. This is much more like a single execution tree. So this is a single query just written as if it is multiple queries. So what that means is that actually we have, like you see here on the side here, an abstract query tree that gets automatically inlined all the uSQL expressions to a single execution model. The benefit of that is then we can optimize that globally. So that means if I have an expression at the end of the script that has a predicate, that predicate can be pushed up towards the top to be as close as possible to reduce the amount of data that needs to flow through the script, for example. In addition, we get at the job level, the optimizer and job manager can determine how much scale out there actually is, and then the user can also set like the maximum degree of parallelism and therefore steer kind of the execution. The actual physical execution plan looks a little bit like the colorful plan down there, which gives you a lot of visibility into kind of what is actually happening on the scenes. And we'll go into detail into analyzing that and taking a look at that as we go through the examples. So if I go and take a USQL script, how do I actually execute that and how does that go through the life cycle? I submit my script and then basically the compiler takes the script, takes some catalog information, obviously the files as well that exist, and creates a plan, or an abstract syntax tree, basically. That then gets passed on to the optimizer, and sorry, there is some issue here with the animation. We'll fix that in a second. Gets to go to the optimizer. The optimizer creates an optimized plan. Then as part of the plan, you will get an optimized tree. Now that tree gets passed to the stage CodeGen component. So what that does is it now decides, based on which code gets put together into a single node, and it creates a program for that. It basically compiles the abstract syntax tree after the optimization into C++ and C# code. And then that gets, as a whole, passed to the job scheduler, where it waits in the queue until all the resources are available. And then once the resources are available, the job manager starts executing the job by vertex scheduling these code fragments, these code units, on different containers, which then are executed in the USQL runtime. The actual allocation of these containers is done through a Yarn layer that we basically are sitting on top of. Each one of those containers has local storage. So the initial vertices or nodes, they will be reading data from the data lake store itself. That's the extract phase. And after that, all consequent nodes will be communicating with each other through local storage. So you're not writing back into the data lake store until the end, where you then basically go and process data as an output. And at the end, you might also write objects into the catalog, for example, if you have DDL statements or add partitions or something like that. So this is kind of the overall workflow. Now, if you actually look at the job execution, there are different phases that you see when you see a job execute, and we'll show that in a minute as well. The first phase we call is the preparation phase. The preparation phase includes compilation, optimization, and CodeGen. That phase you don't pay for, so that's a phase that we will be eating the cost, and which is basically when you compile the job. So if you have a compilation error, you're fine. You will never be charged for that right now. Then there's a short phase, which is hopefully short, but can take some while if you are having a lot of jobs running in your account, that we call the queuing phase. And then afterwards, you have the actual execution phase, during which you actually read and write data, and you're executing, etc. And that's obviously one of the phases that you're getting charged for. You're not getting charged for sitting in the queue either. And then finally, once the job actually finishes the execution phase, the results have to be finalized. That means the data, the files have to be committed, the tables have to be committed, etc., so that we actually have a little bit of an atomic behavior of a job. And what that leads to is basically the finalization phase. Now, you're also paying for the time that you're sitting in the finalization phase. So basically, execution phase and finalization phase is what you're getting billed for. So now, while you're doing this preparation phase, the compiler, during compilation and optimization, is taking the metadata and is taking the data that he has on the store. And if I go and, for example, reference assemblies, or if I deploy resources, I basically compile the C++ and C# code into managed and native DLLs. I create the algebra file that says what is the actual kind of operational tree that I'm operating on in that specific vertex. And then I load all of that together with the system files, together with all the additional resources like that I specified in deploy resource, and build a package. And now I have one package basically per vertex. And that will then get deployed. So let's take a look at the job scheduling and execution. And for that, I will just show you a job that we have been running inside our big data system. So let me find that quickly here. I think it might have been in this one here, yeah. So what you see here is basically the job graph of a job. Let me quickly zoom in here. Up here you see these 4 phases: preparation, queuing, execution, and finalization. Now this job took about 47 seconds to compile, sat in the queue for 7 seconds. That's kind of the standard thing that's just passing through. And then it ran for about over 7 hours. So what did it do in 7 hours that it took that long? Well, the first thing we can see down here is, for example, how much data it actually read. Does anybody know how much data that is? That's 17.5 terabytes of data, almost 18 terabytes of data that this job read and processed. The actual processing was using about 36,000 vertices or units of work. Now the job graph itself looks like this over here. So let me zoom in into this. And you see it's not doing a lot of, it's not that complex. It basically reads from 2 or 3 inputs here, does some joins, and some additional aggregations in between. Now, in particular interesting is the job up here. This vertex here, let me zoom in a little bit more. Now, this vertex here in itself did 6,300 vertices. Now, you see these boxes here. The boxes are what we call stages or super vertices. What they do is they give us visualization of all the vertices that are doing exactly the same work on different parts of the data. So what this means is that I had, in this extract stage, I had 6,400 vertices doing exactly the same work on 6,300 different partitions of the data. Overall, this was reading 4.4 billion rows, and it was basically reading about 4 terabytes of data and writing 2 terabytes of data as part of the processing. Now, what did each one of these vertices do? I can double-click on this, and then I actually see what this was doing. Now, in this case, this was a very simple vertex. It was basically only doing an extract statement of a custom extractor that my telemetry team built that was just reading the files and then producing these rows. So a very simple plan in this case. Now, of course, further down, for example, there is more going on. So one thing that I can do now with the tooling is, after looking at the job, let me zoom this back down so that we can see kind of everything a bit. I can download the job profile, and I can play back the job. Obviously, I don't want to play it back for 7 hours, so the playback is always done within about 30 seconds. So it's now running the job, and I can see already where the hotspot is here, where I spent most of my time. I can also go and change the actual, oops, let me increase that a bit in size again. I can change the color scheme a little bit, and I get basically a kind of a visual clue of which of these stages have been using most of the time. So in this case, again, it was an extract phase up there of the 4 terabytes of data that I was reading. So obviously, now I kind of know where I probably spent most of my time and how I can go and optimize by, for example, going and optimizing that custom extractor that I've written. Furthermore, I can also take a look at, for example, job diagnostics. So we are, as part of the tooling, looking at the job to identify a couple of interesting behaviors. The first behavior is there data skew? Now, in this case, there was none, and we'll go into more details what data skew is. Similar to data skew, I could also have time skew, which means certain vertices run much longer than others on the same data. In this case, again, I don't have that problem. And then I can look at resource usage, vertex execution information, such as did I have any timeouts happening or like overuse of memory or so. And in this case also I don't have anything. Or do I have warnings or something like that? So nothing interesting here, but let's take a look at the job usage. One thing I noticed here is that I process a lot of data, but I only specified a degree of parallelism of 50 for the job. So that means I was only scaling this out to a degree of parallelism of 50, even though just that one vertex had 6,300 vertices that could have run in parallel against the data. So why didn't I specify more, for example, to make it faster? For that, we have this resource usage view here. What this, what the resource usage view gives me is basically kind of a view of what is actually happening while the job is processed. So you will notice on top there you have a blue line, which tells you what was the allocation that I gave to the job, which was 50. And now you see the red line is actually how many jobs or how many vertices were running at any point in time within the limit that I have allocated. So what you see here is that the red line is very close to the blue line, which is good. That means I'm actually making use of the resources that I have specified. On the other hand, the green line kind of tells me how many nodes are ready to be executed but are waiting for actually getting something. So if I have the green line too high, then that means I'm basically under-allocating my resources. And you kind of see that happening in the first half of the job. Like up until about 5 hours or so, that's pretty bad. But let's see what I could do. And for that, we have an AU usage modeler up here. So if I click on that, this now gives me the ability to do what-if analysis based on the observed behavior of that job that I just loaded. So what this is telling me now is that if I would have given almost 7,500 AUs, I would have been done in 1,600 seconds, which is about 27 or 28 minutes. So I would have been 14 times as fast, or more than 14 times faster than I was in my actual execution, but I would have to spend, 150 times or 160 times more resources to do so. Is that a good return on investment? Well, it depends. If I have an SLA that I need to answer that question or run that job within half an hour, then yes, I have to spend the money, I have to spend all those additional resources. But if I want to be cost effective, probably not the right investment. And why is that not the right investment? Well, let's take a look at this thing here quickly. You notice that I have this huge spike at the top at the 7,000. But then afterwards down here, I'm not using any of the resources anymore. Now, however, the way that you get charged when you're running the job is you're getting charged for the area underneath the red line for the duration of the job. So that means you're getting charged for all of this, even though you are not using it. So this is going to be a very costly job if you're specifying it with 7,500 AUs, even though it's going to be very fast, but you will be spending 7,500 times half an hour times $2 an hour if you do pay as you go for that job. So that's about $7,500. If I, however, go with 50, then I pay 50 times 7 hours times $2 an hour. So then at that point in time, I pay, what is it, 350 times 2, $700. So I'm like a factor of 10 cheaper with that job. Now I can do additional what-if scenarios. So what if I, for example, give 700 here, so a tenth of this. And I see if I give 700, I'm running within like 2,700 seconds. I'm still faster than with, obviously, with 50, but I'm still kind of wasting some amount of money there at the end. So I can basically go and do some what-if analysis here. What you see here is also that I can use 200 down here. So if I maybe change this to 200, my job might actually be pretty cost effective. So I should probably have run that job with 200. That would have been done in about, what is that, 100 hours. No, sorry, 100 minutes, or 1.5 hours instead of 7 hours. That will probably have spent about the same amount of money, a little bit more expensive. So these are some of the kind of ways that we can use the tooling to do analysis just for doing cost analysis of the job. Now, another thing I can do is obviously and actually go and look a little bit more into the behavior of the job at the actual vertex layer. So for that, I go back here. And I can go and down here look at something that we call the vertex execution view. So let me zoom in quickly so you see that down here. So let me click on that. And now that gives me basically a view of all the different vertices, how long they were running and when they were running, etc. How much data they were reading, etc., etc. Now, these are 60,000 something, so I'm not going to look at them all at once. I could download that into an Excel spreadsheet and do a lot of interesting analysis. One thing I can do here is to make it simpler, is I can choose the critical path. And if I choose the critical path here, I'm basically getting the job here, execution of the nodes that are really taking the longest time. And so one thing that you notice here is obviously I have an extract that takes a while, that is actually running only for 16 seconds, but it was waiting for all the other extracts to finish first. So basically everything before was basically other extracts. And then I have a pretty expensive cross-split operator here that reads, 11 gigabytes of data, writes 12 gigabytes of data, and runs for about 15 minutes. So if I go back into the earlier view here and look for these SV11 cross splits, I think that's down here, I can open this, and now I see what the query plan is here, so I can zoom in a bit. And so now I basically see here there's a hash join here that is happening, some additional processing, which is a sort, then a filter, some special validation processing is happening here, and then here, down here, I have actually the output that writes it into a table. That's kind of what SSStream output means. It's writing it into a table. So these are kind of like the low-level operators that you're kind of familiar with from a SQL query plan, except for obviously these are operators that run inside the data lake as operators. Some of them are the same or similar to a relational operator. Some of them are specific to the data lake. So this is just giving you a very kind of simple way to kind of get started with the tooling to analyze a job. So let's go and recap some of these items as we go along. As you have noticed, you have a lot of kind of information just on the left-hand side there that kind of tells you what was the job submitted as, how much work is actually done, etc. One thing I would like to point out is that 1 AU, which is the degree of parallelism that you're specifying there, is currently mapped to a container that is implemented as a Windows VM with 2 cores and 6 gigabytes of memory and some hard drive space. Now, the 6 gigabyte of memory is not all available for you if you like write custom extensions or so. About half of it is used by the system itself to flow your data through the nodes, etc. And then the other half is split up into the operators. So if you have a UDO has currently a limit of about half a gig. So if you use more memory, you will actually get an error message. But that will allow us then to pack potentially multiple UDOs into a single vertex. And we are working on giving you options to improve that, both in terms of number of cores and in terms of number of memory. So that should become available sometimes this summer. So now let's quickly go through the plans again. So you are all familiar with this, I think. This is a SQL Server query plan. Now, SQL Server query plan, as you see, only has the operators there. It might give you some information about parallelism if you're running that on a multi-core machine, but it really is a single-level plan. In USQL, the plans is 2 levels. The first level is basically talking about the stages. So what happens now is that you're taking, in this case, that 11 terabyte input, and you are now scaling it out over the first stage, which is the read stage or extraction stage. Then you have a set of stages that follow, that process the data as it goes through, down to the point where you actually write out the results. This is what's called the Dryad stage graph model. This is based on Microsoft Dryad, which was kind of a competing version of what MapReduce was back in the days. And actually, the Dryad stage graph model is kind of underlying both the Spark processing model as well as the Azure Data Lake USQL processing model. And then basically what we do is we visualize this graph in this tree form there. So you will notice we have the inputs at the top and the outputs at the bottom. And then we basically have these individual stages running in parallel to each other there. And then when we look at each stage, we see, for example, how many vertices they contain, how much data they read, etc. And we can also drill in and actually see the actual query plan. So that query plan that you see there is kind of akin to the query plan that you see in SQL Server. Again, this is just recapping the information that you have seen. One thing that I would like to point out is, and let me ignore that quickly, I was hoping it was going to go away. One thing that you notice here, there's like this orange sliver at the end of the vertex there. What that means is that some machines actually had failures while we were executing the 6,300 vertices. And they were failing, and then we retried, and we succeeded. That's because the job succeeded in the end. So our execution model is actually fault tolerant against, for example, things like maybe a bad domain controller on one of the VMs, or a bad memory allocation on the physical machine on which the VM is, etc., or a disk is full, things like that. And we will be reallocating the vertex onto a different container on a different machine and basically then make this job succeed. Now, this is just some what I call query graph art. So this is just a job that is running within Microsoft. This one ran back in 2015. And you can see how complex the job graph is. So this is a very complex script that they're running. And the interesting part here is that it basically was, again, doing a lot of reads. You see that one particular stage there had 8,000 vertices. It did run definitely not for 41 days, because the overall job duration was 41 hours. But just this one vertex there did work for 41 days. Just scaled out, in this case, probably scaled out to several thousand nodes at the same time. This is another one. The thing that I want to point out here is how much data is actually processed. So if you were impressed with the 17 terabytes data that I was just running earlier, or showing you, this job actually processed over a petabyte of data using 640,000 vertices. So this is not just massive data, as Adam mentioned this morning. This is ginormous data processing. Now, one thing that I want to point out is that one of the interesting beginner errors that we see when they're using uSQL and Azure Data Lake is that they just go and say, let's move the slider over to the max, and then I get the fastest job. But that's not how you actually have determined the performance and the scale out of your job. The job has an inherent scale out. And that inherent scale out is determined by the size of the input data and the partitioning of the input data. Like if you have a table, for example, how many distribution groups it has, or something like that. Or if you have CSV files, how big the CSV file is, because if you have a 1 gigabyte CSV file, then you get 1,000 partitions for that. Furthermore, the parallelism also gets determined by the operations. So for example, if you do a join, an equi-join, we probably can scale that out because there are efficient parallel scale-out algorithms for executing equi-joins. However, if you do have a cross-join, at that point we are probably not very good at parallelizing, because the cross-join might need data from every single node to do the join, and at that point in time you have a single node which limits your parallelism. The same for ordering. Any order requiring operation potentially has the risk of giving you a bottleneck inside your query plan. And the same with reducer. If you have data that you need to summarize, like an aggregation or by writing a custom reducer, you have to distinguish between reducers where you have to get all the data into a single node, or reducers where you actually can partition the data over multiple nodes. And it's kind of advisable that you try to find some way of partitioning the data. Last but not least, you can also influence the scale out with some of the hints. So for example, the optimizer is not very good at hinting your file size row numbers. So you might be able to say, might be able to hint how many rows you're expecting out of that extract statement, and then that can impact how the processing gets scaled out. There's also a partition plan hint that allows you to repartition the data as it flows through. However, like with any other relational plan hint, it only works if the plan space already includes a plan that would be satisfying that hint. If you can't find a plan inside the plan space that it generated, then you basically will get a failure. So normally I kind of advise people not to use plan hints, but data hints, because data hints are just helping the optimizer get better statistics. So what does the AU allocation do then? So what does that slider do when I submit a job? It actually does not specify how far you scale out. It will give you an upper limit for the scale out so that you can control the cost. Remember that job earlier? The inherent parallelism of that job was 7,400 something nodes in parallel at its max. But you don't want to run with that high degree of parallelism because it's expensive. So you go and lower it to control your cost. Now, the problem is, if you overspecify your AU allocation, so let's say I have a job that could run with 10 AUs, but I say 50, I'm actually going to pay for the 40 AUs that I'm not using for that job, because I currently have them reserved. We're working on making that a little bit better for the cost experience, that we try to estimate what a good number could be at the beginning of the compilation phase, during that preparation phase, and then give some of those AUs back, so that you get charged less if you overspecify, because some customers had some really good, interesting use cases for actually overspecifying, and so now we are trying to make that possible. Another thing that I would like to point out here is that this critical path analysis is very interesting and very useful, because it actually allows us to potentially pinpoint some place where we have to go and take a look at the code, and then, for example, improve our C# programming or improve our USQL programming to make the job go faster. So now, how do we tune our USQL jobs? I already gave you the demo for tuning for cost efficiency. That's basically going into that tooling that allows me to look at different graphs. Here is an interesting graph. If you look at these two red-marked items, we see a lot of high degree of parallelism here. We go up to 1,000, but sometimes we go down to 1 active vertices at a time. So this is something that is always good to understand, because it means that I might have a need to go and look at the job and see if I potentially need to cut it into multiple jobs, and then basically at that point in time I might be able to get the first thing there done with 700 AUs or 500, and then the next one with 200, and then the next one with 1,000, and I can better control cost. Alternatively, it also might mean that I need to go and think about the partitioning strategy and my operations, and maybe I should write the job in a different way, and I'll show you an example of that a little bit later. And we have the usage modeler that I just walked you through, so that kind of gives you a way of testing out your job performance going forward. So now that I have looked for tuning for cost, let's look a little bit more about tuning for performance. Now, before I do that, you have to understand what you actually operate on and what are the data containers and the data representation that you might have. All of them impact the performance, the scale out, and of your jobs. If you operate on files, we basically have different types of files. Files are, underneath the covers, always split into extents that are between 4 megabytes and 250 megabytes, depending on how you potentially loaded the files in using the SDKs, etc. Now, if the file is splittable, and that depends on the data format that is inside, so the kind of logical information inside a file, we normally try to split the file into 250 megabyte extents that are then 4 at each go into a vertex. So, for example, if I have a splittable format, such as a row-oriented CSV type format, I can go and basically split 1 gigabyte into a vertex, as I just described, and I can operate on it in parallel, because each split is more or less independent of any other split. There are some small feature differences, like about headers, and if this row doesn't quite fit into the extent, etc., and we kind of handle that for you. However, if I have non-splittable data formats, for example, JSON, XML, Avro, etc., which are data formats that I need to have the hierarchical context available for me to actually make sense out of the content, then it cannot be parallelized. And then I have to write an extractor, excuse me, that uses what we call atomic file processing equals true. So what does that mean? Well, that means first that each of these files in its entirety gets passed to the vertex. So that means you have to be very careful that that vertex doesn't get too overloaded with the data. As an example, if I have, let's say, a 50 megabyte JSON file, and I want to parse that into a row set in my extractor. Now, if I do that with a reader interface, I can run through the file, and I can create up my rows, and I can spit out the rows as I go along, and I'm probably fine. If I, however, load it into a document object model inside my memory, I can get up to 10 times as much usage, memory usage, as the original textual representation of my JSON document is. At that point in time, I go 10 times 50 megabytes, and I might actually blow out of my half a gig memory limit that I have inside my UDO. So, and of course, all of this needs to be taken into account also in terms of performance. Now, with unstructured files, we have a feature similar to how Hadoop is operating in terms of partitioning files into directories, etc., that give you the ability to partition files into directories and naming schemes, and then use what we call a file set to do more semantic partition pruning without having to understand the context of a file. If you want to be much more performant and make advantage of clustering and partitioning and distribution groups, etc., meaning anytime we want to read the data more than once, in my opinion, we move the data into what we call USQL tables, which then gives us much better information for the query processor to process on, including statistics for the optimizer, if I create statistics on it, native scalar value serialization, etc. So there's a lot of benefit of tables over just standard files because it gives us much better performance for processing. So let's take a look at this. The first thing I would like to go and talk about now is the loading and querying of unstructured data. One of the promises that we have inside the data lake is the ability that we can store everything in its original form. Now, unfortunately, that's often quite misinterpreted by some of our customers, I noticed. And that's in the following way. Many things think that, well, what I have is I have a single event. That single event comes in as maybe a JSON document, Avro document, XML document, whatever, or even a CSV line item inside my log. I want to keep that as a unit and put it into a single file. So I create tons of very small files. And that's not really good. Like even in relational systems, when you get an individual insertion, not every insertion gives you a table as a unit. What you do is you move those into rows within a table. So we need to apply a similar concept in the data lake, even at the file level, because we want to avoid that we have too many small files. And just to show you that, I have here one example of a script that is reading some data out of a bunch of files. Now, in this case, these are actually 10,000 files that I'm reading. Then I apply some simple filter on it, and then I output it into my file as an output. Let me see which one that was. No, that was the wrong one. No, that's not the one either. So this one here. So I did execute that job. It took about 1.2 minutes to execute. You notice over here that it was reading 10,000 files. Each one was fairly small. In the end, I read a little bit less than half a megabyte of data, which is still fairly small for us. And I did run it on 51 vertices. So we were clever enough to kind of package these files into vertices, so we don't have just one vertex per file. But it's still 51 vertices. So if I want to get like 5 seconds performance, which is the average time on the vertex there, I would have to run that with a 51 AU allocation, which is not very optimal given that I'm only processing like 0.5 megabyte of data. So what should I do? Well, if I actually packaged the files together into one single file, for example, before I uploaded or so, then the job would look like this. I have the same amount of data that I read, but now I read it in a single file with a single vertex, and the overall execution time in this case was only 24 seconds. So I'm much faster. And now obviously you can observe that even if you're running on your PC, just opening and closing files is taking your time because you have to go through the metadata layer. So the important point here is make sure that you have the right size of files. Now, given what I have told you earlier about how we actually allocate file sizes to vertices, kind of the recommendation is, if possible, if the data format allows you to do so, go between a few hundred megabytes to maybe 4 gigabytes per vertex. More than 4 gigabytes right now probably gives you some issues with memory. Lower than that gives you issues with basically over-partitioning your data and therefore not being as efficient as it can be. So how do I control that when I load my data into the data lake? Oops, that's here. So obviously I can do concatenation outside of Azure. I can make sure that if I use Event Hub, for example, to load data into my data lake or Stream Analytics, that I set the kind of archiving feature in a way that I maximize for large files and for longer durations. Or if I have to more frequently insert, make sure that you have compaction jobs running inside your Azure Data Lake analytics environment to kind of compact the most recent deltas into something bigger before you actually run your big jobs against them. So there's some best practices around that. So I mentioned we can do partition elimination on unstructured files. And so just to show you how that looks like, I have here exposed the file number of my files. Oops, sorry about that. Into a column inside my row set. Now, this column can be used in a predicate, such as the one down here, where I basically say, well, only do that select statement for files between 1 and 50. So that means I get 50 files that I only have to process. Now, our Cree processor is efficient enough and clever enough to take that predicate and push it up all the way into the extract phase, and then tell the extractor only extract the files that satisfy this criteria. Which means instead of reading 10,000 files and then filtering it out, it will actually only read 50 files from the beginning. So that gives us a huge performance improvement. And we can use that for like all kinds of partitioning. I can put multiple like such columns, for example, into my path, and then put predicates on to kind of get the right partitioning of my data. So this is just showing this on the slide here. I'm kind of going forward here a little bit quicker because we really need to kind of make sure that we are not standing too much over time before you get your beer. Now, another kind of hint here is right now we are doing a lot of work on making these file set improvements actually go faster. So we have a few kind of hints that you currently have to specify as feature preview items. Many of them will become part of the product without you actually having to explicitly specify them. For example, the 2 ones that I specify below will be part of the next refresh as default. But for now, it's kind of recommended to put them in to get like really file set improvements. Another thing that I want to point out is, and again, that's a problem of operating on small files, specifically if you have custom extractors running on them. When we create a vertex, your custom code, like all that code that I've shown you earlier in that box for the vertex, has to be deployed onto the vertex. Now, if you give me custom code, that is additional code that I have to deploy. Not only that, I have to do more work because I can't trust your code completely, so I basically have to deploy it on every single vertex creation. While if I just have my own code, I can deploy it once and then I can reuse it. Now, if I have a small file, then that vertex creation time there will be dominating the actual vertex execution time. The actual work, in this case, for example, it takes a few seconds just to deploy the vertex, and then that tiny little green sliver at the end is the actual work that is being done. And that just shows you that in this case, the file was too small. Now, obviously, if you have a single job which only does exactly that one vertex, you don't have anything that you can do to make that go like better. The problem here is really if you have a whole wall of blue of maybe 1,000 of these vertices that all do the same job on very small files. That's when this gets really a problem. And so what can you do? Well, if you package all the data together, then this vertex back here, actually the green will get bigger compared to the blue, and therefore we are more cost effective. So now let's switch over. I mentioned we also have tables. Now the tables actually give me a lot of benefits in terms of performance. Here is a simple example. Let's assume I have a set of click data, and I just want to count the number of clicks per, let's say, top-level domain of the web engines that we are looking for. So if I have a file, I don't know which extent or which part of the file contains which of the domains. So we have CNN, Facebook, and White House here as an example. So if I do that group by, I do a local grouping and aggregation for each of the vertices that I'm running on over the partial part of the data. And then in order to be able to get my full aggregation done, I have to now move the data between between what we call the pods here, or the different vertices. So we have an expensive data movement problem now. This is the general problem that any big data system scale-out architectures have. You want to avoid to move data between the local nodes to other nodes, because that just means a lot of bandwidth gets used, a lot of time gets spent on that, and it's expensive. So what can I do? Well, I don't trust anything that you tell me about the content of your file, because it might not be true. However, there is a way of making it true, which is that you use tables. If you specify tables and say, for example, each domain gets its own partition or distribution, then the optimizer relies upon that metadata information and, for example, can avoid that expensive shuffle by just doing the local aggregation. So what that means is that you want to actually use distributions to scale out. I'm skipping the demo because otherwise I'm not going to get through here. But what I want to show here is basically that we have the ability to give you different mechanisms for distributing the data in interesting ways. So you have hash partition, direct hash partition, range partition, etc. You choose the right partitioning to give you the most optimal performance for joins based on partition sizes, filter selectivity, and what partition elimination you can get. We also give you a second level of partitioning that again can help you with partition elimination, as well as with what we call data lifecycle management. So you have basically two ways of partitioning your data. So let me give you an example. Here is a table T, has a couple of columns, and now I say it's partitioned by date. Within each partition, I subpartition the data with a distribution scheme into 4 distribution buckets with a hash function. And then within that, I cluster the data based on the hash key and some additional column. So what that means now, let's assume I created 4 partitions for date 1, date 2, and date 3. They're each individually addressable. And now I basically insert data. Now, in this case, I assume the data is not quite fully the same between the different partitions. Some of them might have a little bit more and a little bit less distribution buckets here. And then within those, the data gets basically clustered based on the ID and then based on the column as well. So that way I get like locality of the data. If I now, for example, look for a certain date, a certain ID value, and a certain column value, I only have to basically pinpoint myself into one of these rectangles there. I don't have to read anything else because I have enough metadata to pinpoint the region that I have to go and read the data from. The same as in index lookups in like standard relational tables. Now, physically, they are mapped into files inside a catalog directory inside your Azure Data Lake store. And these files are like have GUIDed names. And you get basically one file per partition. And then within each one of those, you basically then have what we call extents, which are then basically representing the colored hash distribution buckets. There is at least one extent per hash distribution, there potentially more if it's a really large one. So what are the benefits of table lookups? You get faster table lookup of the data. You get better localized scale out if you use the same and well-designed distribution group, for example, or distribution scheme. You can actually reduce the cost of AUs for your job because suddenly the operations might be done with less AUs more efficiently. And you can basically also use table partitioning for data lifecycle management and exploration, etc. You should not use the table if you're always reading all of the data and if you're only reading it once, because at that point in time, there is no benefit over just reading it from files. If you are not quite sure which layout to choose, etc., we recommend that you take a sample of the data, and we have sampling functions as part of the language, to kind of build some what-if scenarios and like do some testing to see which works best. This is just some more detail here. One interesting part here is that, for example, the optimizer can make certain use of certain knowledge. So for example, if you have a range distribution, make sure that the distribution key is a prefix of the cluster within, because then the optimizer knows there's a global ordering of the data that it can use to further optimize your queries, for example. Now, the benefits that you have is that partitions are always addressable, either directly through the query, or in the case of the actual high-level partitions, also by explicit statements. So here's a kind of an example. You create a table, and then you say partition by. You actually create explicit partitions, a little bit similar to what you do in SQL Server for partition tables. And then you load partitions either dynamically by saying just dump the data in, and we automatically route, or into static partitions where we say, for example, move the data into a specific partition or move the data into the partitions and into a specific location if the data doesn't fit. Now, one thing, once you have tables, that is very tempting is that you do a lot of inserts. And we kind of warn you against that. So we basically tell you to not go into like table fragmentation and over-partitioning. So what is table fragmentation? Every insert statement creates a new insert fragment, which is basically a physical file that looks like that partition file that we've seen earlier on the slides. So why is this bad? Well, every insert fragment contains data, again, in its own distribution bucket. So the query processing doesn't get the localized access anymore. Now it has to look at distribution buckets in more than one files, which obviously is inefficient. And also, we do have a limit right now of like 3,000 table partitions and insert fragments per job. So if you're reading too much, then you're basically running out of space. So what if I have to add data incrementally? Well, what you should do is you should batch them into the table by having larger insertions happening at the same time instead of a lot of small inserts. And use alt-table rebuild or alt-table rebuild partition to regularly maintain your fragmentation, reduce it, and keep the performance up. So I think we are kind of coming towards an end, so I will be quickly going up and scroll down to the end of the presentation. Come on. And kind of point you to some, what the hell happened here? And kind of basically give you a list of additional resources. So all of that information, as I mentioned, and the information that I didn't get to at the end because of time, is available, is going to be available on my slideshare.net account, so you can go and take a look at that in more detail as well. We also have continuous education on our Microsoft Virtual Academy. I'm actually planning on recording several of these sections that I've given you today over the next 2 months as individual small sets. So you can take a look at those at your leisure at that point in time as well. Otherwise, any performance questions, etc., you have our forums and our Stack Overflow place. Just as an example, recently somebody had the standard problem of having a fact range entry inside a fact table where it says the fact is valid from begin to end, and he wanted to pivot that into 1 row per day. Now, the way to do that in industry standards is that you do a join against the dimension table that contains a day per row, and then you do a join with a between clause. Now, the problem is there is no efficient scale-out algorithm for that. So what you have to do is you have to do a cross-join with a where predicate. So the cross-join basically gets all the data into a single node. So if your fact table is huge, then that gives you a very inefficient kind of processing. So what to do in this case is actually to use a cross-apply with a C# expression that takes the begin and end and then dynamically creates one value per day interval. And because you're using a cross-apply now, you have a single row that then explodes into multiple rows, and that can scale out without any problems. And that was a kind of a question that we got on Stack Overflow. And what this just shows is that if you are optimizing your queries, sometimes it counts for understanding whether the query really needs to be written in a textbook way or whether there is a better way to actually formulate the query. So with that, I don't want to keep you from beer and the BI Power Hour. And so thank you very much for attending the session. I hope it was worthwhile. If you have any questions, I'm staying around a little bit longer while we are also drinking the beer. Thank you very much.